I grade your exams, and you can request a regrade online through Zoom if I missed up grading part of your test. The last one was the hardest problem, and most people had difficulty with it. So we could discuss it real quick if y'all want. And let's see here. Of course, at this point, you've had time to think about it. Maybe you've already figured it out. Let's see, remind myself of the problem. So on the midterm, number 5, you have this surface, and there's a point P, and at this point P, we can look at different cross sections, right? We have our unit vector u, and then we have this little u, and this little u is equal to cosine theta. Let me just make sure I use the notation of the problem. U1 cosine theta, times U1 plus sine theta times U2. And what you're told is that if you take the surface M, and then we look at this right here, and this is defined to be the plane at angle theta, what we're told is that M intersect the plane at angle 0 is a circle of radius 2, and not only that, but also the intersection at 60 degrees, which is pi over 3, and 120 degrees, which is 2 pi over 3, are all circles of radius 2. Okay. So in particular, can anyone think of, at this point I'm sure you can't you think of a surface where when you intersect at these 3 angles, you get a circle of radius 2, sphere of radius 2, right? And so you figure that's a reasonable guess. Now, by the way, just in general, when someone gives you a problem, you're trying to visualize it, right? And, so at least we know there's one example, right? A sphere of radius 2. And so in part A, it asks you to say, what is the shape operator of the point P for any tangent vector V? Now, let me just give you all a little test-taking tip and strategy. I think most of y'all got part A. But the fact that I asked the question means there must be an answer, right? Which means that you can determine the shape operator uniquely. But we know that as far as we know that a sphere of radius 2 satisfies the criteria, right? And so, whereas there could be many surfaces that have this criteria, a sphere of radius 2 has it, and the shape operator in that case, right? The shape operator of a sphere of radius 2 is just multiplication by minus 1 over r, if the unit vector is pointing out. So it's minus v over 2. So that's the correct answer. Now, there was some question about getting this sign right, whether it's a minus or a plus. And so that's just a matter of calculation. I'll refer you to that. But let me tell you how I think of it, how I remember it. The definition of the shape operator, of course, has this weird minus sign there. Okay, so anyway, it's completely arbitrary, historical. And so it's just the derivative, it's the negative derivative of u, right? And so if I think of, just visualize how the vector, if I go to the right, then the vector becomes this, right? The difference in the vectors is that, right? And so when I go that way, this covariant derivative is in that same direction, right? So this derivative is in the same direction as v. And so, therefore, the minus sign is going to be the opposite direction. So this minus sign here is that minus sign there. Otherwise, this would be in the direction of v. Does that make sense? Okay. So that's one way you can remember that. Just sort of catch that picture. And then really what this problem was about is recognizing that we can define the normal curvature k of theta to be u of theta dot product the shape operator, right, of u of theta. And now we cannot assume that u1 and u2 are eigen vectors of the shape operator. All right, it doesn't say that in there. It just says there's some u1, u2. So I took off a few points if you assumed that they were eigenvectors. But more generally, what you can do though is assume they equal something, right? The shape operator applied to u1, let's say, equals a u1 plus b u2, right? And then the shape operator applied to u2 is equal to c u1 plus d u2. And actually, b equals c because this is a symmetric shape operator, but that doesn't matter. It turns out because what we can argue then is that therefore this k of theta, when you work it out and plug in everything, is you're going to get something of the form a sine squared theta plus b cosine squared theta plus c sine theta cosine theta. That's the point for some a, b, and c. Okay. Plug in, do the algebra, and simplify. And the picture is that when you graph this, it's a sine wave, a shifted sine wave. Okay. And the period is 180 degrees. So let's see here. Was that one period? Okay, so that would be pi right here, right? And then what we're saying is that for 3 different values, it equals the same value. So notice how when you draw, if I draw a line in one period, I get 2 intersections, right? So any horizontal line intersects usually twice, unless I'm at the very, very top and the very bottom. At the very bottom, intersects once, right? Sort of like a double root, right? And so the point is, if I have a genuine sine wave that with positive oscillation, there's no way to have 3 values. Because what we're given effectively is that k of theta, because of these intersections, we know that k of theta at 3 different values. K of 0 is equal to minus 1/2. K of 60 degrees is minus 1/2, and k of 120 degrees is equal to minus 1/2. Okay, so it's down here. Okay. And so, but I just want to make the point is when you have a sine, when you graph a sine wave, and by the way, this is a sine wave. You're like, really, it doesn't look like a sine wave because you got sine squared. But remember, they're half angle formulas, right? When you multiply sine waves, you get other sine waves. And so, you know that if you specify 3 values, right, it must be actually a constant sine wave. In other words, it's kind of trivial. Oh, I forgot to say plus a constant d. No. Sorry. When you do the half angle formula, there's a constant d that comes out, right? So in other words, if a equals b, then the height of this magnitude is there's no oscillation. It's just a constant, right? If a equals b, then sine squared plus cosine squared equals 1, right? And so you just get a constant. Okay, and so if you, but here's the point: is you have 3 unknowns, a, b, and c. You have 3 equations, 3 unknowns, 3 equations. You solve for a, b, and c. And what you get is that a equals b equals minus 1/2, and then c equals 0. Okay. Now, by the way, if you use your half angle formulas, this also equals 3 other constants. Some constant a plus some constant b times sine 2 theta, plus some constant c times the cosine of 2 theta. And then in that case, if you were to solve it that way, then a equals minus 1/2, and then b equals c equals 0. Right, and then in the second way, you can see, like it's saying that there's no oscillation; it's just a constant, and that's the only way you can have it be the same value in 3 different points. Okay, so that's how you solve that problem. It was definitely the hardest problem. I think the other problems were reasonably straightforward, and that one was a bit challenging. And that's kind of the idea of these exams, is to give you something to challenge you a little bit. And also to make sure you all say modest and humble, right? Because actually I was very happy with the results of the exam. I thought everyone, in my mind, everyone got an A or a B. And so if you're wondering what's an A, 50 or above maybe, and then let's say out of 60, and then 40 or above we'll say is a B. And so everybody was in the A or B range. Any questions? So that brings us, by the way, I have your exams here. If grading exams is an art form. I was trying to, I do them one problem at a time. Is one thing that's nice about Gradescope. And so all I can say is I was consistent. Okay, as consistent as I could be, right? On number 5, I got a lot of different types of things. Oh, let me just comment on number 5. What do you do when you can't figure it out? Here's what I'd like to request. When you can't figure it out, it's still nice if you can argue coherently. Okay, I'm not looking at anyone. I don't remember. By the way, I grade it blind. I don't even know what you wrote. If I'm looking at you and you're like, oh, what is he looking at me? No, I grade them blind. I don't even know what you wrote. Okay, you guys understand? But let me say that I'm going to say probably over half most people didn't get number 5. I don't know if maybe one or only 1 or 2 people got number 5 completely. And over half probably had answers that were really hard for me to try to understand what was being written. Okay? So like when people, like, in other words, it might be super easy for me to understand what you wrote on the first 4 that you got, and then comes number 5, and it's pretty obvious you don't know what the answer is because I can't even understand what you're saying. Do you guys understand my point? Okay? It becomes incoherent, right? Now, so I think actually, now here's the thing, I'm not promising you get more points. Like if you're coherently wrong, that still might not be more points. But I think that's better for you. And so put more English in even if you're trying to figure something out, put in more words to say, and I actually could even say this, and I think this might be the explanation. Go ahead and say, I'm not sure, you might even say, okay, I don't think I got this problem, but here's what part of the problem I think I do understand, or here's how an approach that I think would work. But add some words so that I can understand what you're at least attempting to do. Like, like for example, if you got to the point and you said, look, there's 3 equations and 3 unknowns, I suspect you could solve for A, B, and C, right? Oh, okay, I see what you're doing, all right, and that's actually, if you can make a comment that's half right, half wrong. I mean, give me a chance to give you partial credit, I guess, is what I'm saying. But even beyond that, it's just, I think it's a good sort of habit. Now, does any of my notes sort of look like chicken scratch sometimes? Sometimes, but I also know that I'm being naughty and I shouldn't do it. Yes?
Actually, for this one, so since we know that the period is like 180 degrees is pi, I seem to remember in class we had some argument that because of that fact, if it's equivalent to the same value at 3 different points, it must be constant.
Yep, you can argue. It's already true. So, like, I would accept that as an argument. Someone could just say that, and that is a fact, right? A sine wave that has the same value at 3 points must be a constant, right?
Yep.
Yeah. So, and by the way, if you have that argument in your paper, and I didn't see it, and I didn't give you credit for it, then just talk to me later, and I can correct the situation. Because sometimes it's hard to see. That last problem was particularly hard to grade, let me just say. Okay. On the other hand, if you're like, hey, how come you took off so many points? I was mean to everyone equally, okay? Just realize there's a fairness to it, all right? I was equitable? Is that what fairness means? Okay. I was equally harsh in my grading. Or not harsh, right? It's all on a curve, right? It's not like, and so by the way, it's certainly not the case that I think of 90% above as an A or something like that. I don't have that. I just grade it in a consistent way. And then we scale everything at the end. As I said, roughly 50 or above I would consider to be an A. Maybe 50 would be an A minus or something. Okay, 49 would be a B plus. All right, so if there are no other questions, let's go on to new material. Like I said, on the whole, I was actually pretty happy with the midterm results. Okay, last time we talked about soap bubbles, and then we got into geodesic curvature. So just to summarize what we've done in the last two lectures, K equals some function of E, F, and G, right? and its derivatives, right? And then, but also geodesic curvature is equal to some function of E, F, and G, and also U prime, V prime, U double prime, and V double prime in the coordinate chart, right? So that's where you have a coordinate chart for your surface. And this is where your curve over here is just U of S comma V of S, or T. I think the book might have a T there. Tell you what, I'll put T's now because yeah, on the board last time I did S, I think, but I'll do T's now because actually I think the book does T's. Because here's the question: it's U of T comma V of T. It's not a unit speed curve in the coordinate chart. It's just we want it to be a unit speed curve on the surface, right? And so anyway, you can and by the way, you don't even have to make it a unit speed curve. You just have to adjust the formula if it's not a unit speed curve. In fact, I'm trying to remember now. I think you do have to assume it's a unit speed curve. Yeah, for the form that we derived, if I recall correctly. But there should be a way to account for that. Obviously, like you know how to reparameterize curves, right? So if it's not a unit speed curve, then there's going to be a formula as well. And as I point, the key point is like the actual function isn't so important. It's just that it is a function of these things. And so what we're going to learn later is that actually the integral over something that's topologically a disk, okay? So, okay, like a potato chip or something, right? They call that M. The integral over M of the Gauss curvature times the area form plus the integral over the boundary of M of the geodesic curvature times the length form on the boundary, that this always equals 2 pi, okay? And that's the first version of the Gauss-Bonnet formula. Now, we have not proved this yet, but I want to point out at least it's plausible because that's intrinsic geometry and that's intrinsic geometry, right? So this is actually an identity that the mathematician ant on the data chip can prove and verify and understand. And you might say, well, how are we ever going to prove something like that? Well, we're not proving it today, and then, by the way, then we have spring break. And then we're going to come back, and then we're going to do some other stuff, and then it's going to be weeks, and it's going to be a month until we prove that. Probably it's kind of ridiculous, actually. Because it's like, oh, we're right there. It's like you can tell I can barely stand it. But the answer is we're going to prove it using Green's theorem. It turns out it comes down to Green's theorem. Roughly speaking, Green, now you might say, well, where does that 2 pi come from? That's the only thing, right? If it wasn't for the 2 pi, this was 0, then I'm saying the integral on the boundary equals the integral of something in the interior, right? That kind of looks like Green's theorem, right? And so it's sort of a pretty clever version of Green's theorem, right? But in some sense, what's going to happen is we're going to take this formula for the geodesic curvature, and we're going to express it a certain way, and then we'll see that as sort of the flux through the boundary or something, and so then that equals the divergence of that vector field on the interior, and that ends up being the Gauss curvature. And there was something else that wasn't a flux, and that integrates to 2 pi. The other thing that doesn't, and by the way, the thing that's going to give you the 2 pi, where that's going to come from, is going to be the integral of theta prime of t dt around the curve. Actually, it's the boundary of n inside the coordinate chart. So we're going to have to use a coordinate chart to prove this. And so if we have a global coordinate chart for a disk, which we can, right? And so maybe this is the coordinate chart for that potato chip, right? This coordinate chart has a UV axis, right? And then you can look at the angle, right? Every point there's an angle, right? That angle right there, we call it theta of t, right? And so therefore there's a theta prime of t. But what does this equal? This is equals, if you integrate over any length, the integral of the fundamental theorem of calculus tells us this is delta theta, right? How much does theta change, right? It's a total change in theta. But when you go around once, theta increases by 2 pi, doesn't it? And so that's where that 2 pi is going to come from. Okay, so that's just a little foreshadowing. Okay, so now let's get into geodesics. Let's talk about that geodesic curvature. Let's talk about geodesics. That's when the geodesic curvature is 0. By the way, what's an example of a geodesic? Well, it's sort of the closest thing to a straight line, right? So if you're an airline and you have to fly from Salt Lake City to New York, you want to use as little gasoline as possible, right? It's costing you thousands of dollars per flight, right? And so you're going to follow the straightest line. And that's, by the way, given any 2 points on a sphere, just as visualize it, any 2 points on a sphere, you can rotate the equator through those 2 points, right? Like think of a great circle, like an equatorial circle, right? Through those 2 points. Obviously, going along that equatorial circle, right, it's called a great circle, is the shortest distance. But you guys have all seen the maps, so have you all seen all the maps of airline flights? Have you ever seen, like, this is where United States.
Nice.
What is that?
It's supposed to be the United States. I don't know. Not even close, right? Anyway, it's supposed to be the United States.
Oh, there you go.
That's actually pretty embarrassing. I should practice that because it just comes out so bad. But at least you can know what I'm talking about. Let's say Salt Lake City is over here and New York City is over there, right?
What does Maine?
Yeah.
Does Maine really count, though? I have to say. No,
Whoa.
just joking. Has anyone ever actually been to Maine?
I've been to Maine.
I have also been to Maine.
I have too, actually. I think I can. That's beautiful. That's true. Isn't there like a theory that Australia doesn't exist?
Whoa.
I think there's like a theory on the internet that Australia doesn't exist.
I mean, I've been there.
No, I have
No,
too.
you haven't.
Okay, but if you haven't been there, like, couldn't it just be a conspiracy? Anyway.
I could see it being somewhere else being like a conspiracy, but like there's definitely like Australians. Like there are people there who have been there.
Ultimately, you're kind of taking their word for it, right? In fact, even when I've been there twice, I mean, I wasn't exactly tracking the airplane at the time that we actually went to this place called Australia, right? So I'm kind of taking the pilot's word for it.
Could have been Texas.
Yeah, I mean, this could have been a big Truman Show kind of thing, right? Anyway,
Great.
so the shortest distance, you guys know what I'm talking about. It always looks like a curved line, right? The shortest distance between 2 points is like a curved line, and that's not because it is curved. It's because these maps are all distortions of reality, right? You take the curved surface of the Earth, and then you try to squish it down to a flat piece of paper, right? And that distorts things, and then you just get what you get, right? And so happens, this is the shortest distance, though. And it's also a geodesic. And so understanding what the geodesics are is of importance, right? It's of economic importance to airline companies, if nothing else, right? But it's a natural geometric question. What's the shortest distance between 2 points? The answer is a geodesic, by definition. And by the way, these things have zero geodesic curvature. Okay, so that's what a geodesic is. And that's why we call it geodesic curvature, because it's the thing that has to equal 0 to be a geodesic. Okay, so what we did last time is that if we have a unit speed curve, then what you could say then is alpha. Okay, so unit speed curve alpha of s. I use the Brooks notation. Then you remember we argued that's going to be some linear combination of this frame, right? I mean, remember what u is. U is the normal to the surface, right? U is the normal to our surface. Okay. T is the direction of our curve. T is just alpha prime of s. And so, and these are perpendicular by definition. They have length 1 by definition. Take their cross product, and then u cross t will be unit length, and this will give us an orthonormal plane. So therefore, you can think of it as like I, J, and K. And here's a nice little trick, by the way. Remember that I cross J equals K, right? That's kind of definition of the cross product. It's at a definitional level, really. That's 1, 0, 0, that's 0, 1, 0, that's 0, 0, 1. We define the cross product so that this is the case. Okay? But then it also follows that J, if you just cycle them, J cross K equals I, and then K cross I equals J. By the way, J cross I is going to be negative K, because when you switch them, it changes by the sign, right? And here's what's kind of neat, by the way, is that if I cross J equals K, then I can call this I, call that J, and then call that K. You guys get that? Because whoops, got these backwards, right? So this is going to be happy I cross J. So this would be I, this would be J. Okay? So if I think of this as I, and that J, and that K, right? And in fact, I can do that, but it's a rotate I, J, and K, right? But it turns out it doesn't matter. Cross products invariant under rotations. And you might say, well, why is that useful? Well, now, if I ever want to do this cross product that, I can say, well, what's K cross I? I look at my chart and I say, okay, it's J. So this cross product that equals that. Okay, and so I don't have to, I mean, how else would you compute that? It'd be kind of annoying. Okay, so you just got it immediately. Okay, or what's T cross product this? Well, J cross product K is I, so it's this, as opposed to the negative, which would also be a possibility. Okay, any questions about that? Okay, so the next thing we want to do then is yeah, so then if we, but then here's alpha double prime of s, though. Remember that's perpendicular to alpha prime of s because it's unit speed, so there's no term there. And now what are these coefficients here? Well, this is just alpha double prime of s dot product u. That's how you find the coefficient, right? And this is alpha double prime of s dot product u cross t. And then this first thing is what we call geodesic curvature. And then the second thing is what we call normal curvature, right? Okay, so we have names for both of those coefficients. Now, the next thing we want to do is, what if we have a curve, but not necessarily unit speed? Not necessarily unit speed curve. Okay, so it's not necessarily. And it's called alpha of t now. The fact that I'm not using s means that it's not necessarily unit speed. I mean, maybe you got lucky or something, but probably not unit speed. And then we want to compute a formula for that. And so what we want to do is say, well, then alpha double prime of t equals what? Okay. And let me show you what it equals. It's ddt of ddt of alpha. Hard to argue with that, right? But then there's something called the chain rule. And the point is ddt, it can be expressed in terms of dds, but then I have to multiply it by a factor here. And this factor here we'll call nu. And that nu is just equal to ds divided by dt, which is the speed. ds dt, that's s prime of t, that's the speed. Okay? So this is the chain rule here. you all see that? Just put this up here and make put a ds dt. See the ds is canceled and we have the dt. So that's how you remember the chain rule, right? You all see the mnemonic device? I have ds over dt here. The ds is canceled and it works as a fraction, right? That's not. That's how you remember the chain rule, right? It's not actually an algebraic thing you can do because these are symbols, okay? But it's how you remember it. Those symbols are chosen because they're limits of things where you actually can do that cancellation, right? The delta s's and the delta t's, right? Okay. So this new right here is equal to the speed, but we'll just call it nu of t there, okay? And so if you make that substitution, whenever you see a ddt, you can put as nu dds of nu dds d alpha ds, okay? And now let's do a little calculus here, okay? This is still ddt, okay? Taken together, this is still ddt, right? Now if I do ddt, I got to do the product rule. If I do ddt of nu, I get nu prime of t. Times alpha prime of t. So I'm going to say times d alpha dt. Okay, so and this for doing the chain rule, I actually went back to this, okay? This was a ddt, that's a ddt, and so I get that for the first term. Plus, now I'm going to take the dds and apply it to the second term here. And so what I have is nu squared times the second derivative of alpha with respect to s. Any questions so far? And so then what does this equal? This is nu prime of t. So remember what nu is. So this is nu of t is the speed. Nu prime of t is the rate of change of the speed. You might call it the acceleration. D alpha dt, remember that's what we call t. It's alpha prime of t. Right? That's just the vector t. The direction we're going. Plus nu squared times this, right? But that is the same thing as this. So it's nu squared times this stuff, right? So what we get then is nu squared times the geodesic curvature, u cross t, plus nu squared times this, okay?
On that previous line, should you have a d alpha ds instead of dt?
No, because the nu is right there. So this whole operator is being applied to alpha, so it's alpha prime t. That is the same thing as this.
But I thought t was d alpha ds, not d alpha dt.
No, in this context. So once we draw this line here,
Right.
over here, t is just we're getting rid of all the s's. So now we're going to redefine t this way.
Okay.
Yes. So t has been redefined. Thank
Okay.
you.
Yeah.
You're okay. Wait a second. Yeah, that's what the book is doing now. I think. Gosh, good question. Let me see here. Try to make sure. Yeah, I think t is alpha prime of t now.
Okay. So it's not
Yeah.
unit length.
It's not unit length. Is that true?
I don't.
Maybe I don't have my book with me. Did I? 'Cause
Something.
that's what my notes say, but it's like, God, really?
Something seems inconsistent.
Yeah. So wait a second. Gosh, I already mistaken my notes. I've been using these notes for like 6 years.
Like, how do you go from?
Go ahead.
Well, just because you have on the second line, you're taking the derivative with respect to s, right? So I would expect when you're expanding
Okay.
using the chain rules.
Let's just check this, right?
Yeah, sure.
Okay. So, okay. So this is ddt, right? So we get nu prime of t times d alpha ds. Thank you. My notes, let's see here, does this wrong? You know, I went away from my notes just for a second there and I messed it up. Okay, and then S, okay. T is alpha prime of S. So that was wrong there. Okay, sorry about that.
Yeah.
Okay. It's still the unit vector, yes. Okay. All right. And then, okay, then we get nu squared. When this operator gets applied to this, we get nu squared times second derivative of alpha respect to S. Then we, okay, so then we have this T is just the unit vector here, of course. And then we get nu squared times this, right? And so then we just leave it as something times u, okay? Now that something here, of course, is just nu squared times this. Okay? It is. And so I could write nu squared times that if I wanted to. That's correct. But let's say I want to rewrite it a little bit differently. That's supposed to follow the book, and it's their look, it's their book, all right? And the way they choose to write it is to say, look, this alpha double prime of t, we have an orthogonal frame here, t, u cross t, and u, right? And so we could use that. It's alpha squared. It's nu squared times this, but also it's simply alpha double prime of t dot u, right? And they choose to write that way. And there's a reason, because then we can remember them, because we have a formula which says this is also equal to alpha prime of t dot product shape operator with alpha prime of t. Remember that? So this is, again, the same thing as it's normal curvature. It's just that we're not putting a unit vector in there. Okay? Necessarily. All right, so this is our formula for the acceleration vector alpha double prime of t for a general curve on a surface. And now let's study it and make sure it makes sense to us, okay? Remember what geodesic curvature was. Geodesic curvature is how much you're turning left or right. Well, it's still how much you're turning left or right, but you have a factor, up to a factor of the speed squared, okay? And so this is just telling you that if you're going faster, then the acceleration left is more. And that makes sense, right? And let's say you guys are most of y'all have driven cars, right? You probably haven't gone to a racetrack or anything, I hope. Or at least that would be safe, I suppose. Hopefully you're not racing like a racetrack on the streets, right? But if y'all ever, if you've driven a car enough to know that when you come up to a curve, you need to slow down quite often. You can't just go any speed you want around a curve, right? You're going to drive off the road, right? And in fact, the faster you go around the curve, the greater the acceleration. You can feel it inside the car, right? And eventually your car will lose traction and crash off into the woods or something, right? Okay, well that goes up with the square of the speed. Okay, normally we have nu equal to 1, but your acceleration to the left as you turn your car goes up with the square of the of your velocity. And that's what this formula is demonstrating. So if, just a little driving tip, if you, by the way, this is particularly relevant in California and certain other places. In California, if you ever see a yellow sign that says 20 miles an hour around the next curve, you better slow down to 20 miles an hour. They're not joking around. Like, it's yellow and it's like a recommendation, but it's really a recommendation if you want to live. Okay? Because some of their turns, it's a little bit mountainous. Where in Northern California, that's what I'm talking about, right? And like, there have been times where I was like, yep, that the 20 is maximum. That's why you don't want to go any faster than that. I'm from Texas. Everything's straight. There are no tight turns. So I was unprepared for that when I first went out to California. So I didn't crash or anything. I was just noticing that their yellow signs are much more critical than the yellow signs I had in Texas. That's and so yeah, your acceleration left or right goes up with the square of your velocity. This is just your normal curvature, the same as before. But now we have a new term. See, before we didn't have a t term. Right? Remember the t term was 0? But now you actually have acceleration in the direction you're going. How could you have acceleration in the direction you're going? Well, it's because you're increasing your speed. Okay, that's why, right? Oh, okay. How do I? If I'm going unit speed, I can accelerate to the left. I can accelerate to the right. I also can accelerate perpendicular to the surface. I'm doing that all the time if I'm on a sphere, right? But how do I accelerate in the direction I'm going? I got to speed up, right? and that's where the speed increases. So actually this makes perfect sense, doesn't it? Actually, it's quite intuitive. And so in general now, when you have a curve on a surface, you can just compute this, compute alpha double prime of t, and then look at the components here, right? And you'll know, something about your curve. And so what does it mean to be a geodesic? There's a definition for what it means to be a geodesic. And that's, well, let me write it down. Just a definition. So, now what is a geodesic? What is a geodesic? The definition they give here is a geodesic is a curve with constant speed and the geodesic curvature equal to 0. Okay? So two things, geodesic curvature equal to 0 and constant speed. Now what that means is there's no acceleration in the surface itself. The only acceleration is that which you cannot avoid, right? In other words, it's really 0 acceleration as far as the ant could do. And that's really the way I would think of it is, as far as the ant can control who's walking along a path, the ant's following a geodesic if in fact they're going in a straight line. They're not changing their velocity from their perspective at all, right? The only component is this component here, right? These other two things are both 0. Okay, so what's an example of a geodesic? The simplest example would just be a straight line at constant speed, right? So in R2 or R3, you just define alpha of t equals some point p plus t times some point q, right? I mean, that would be a geodesic. If you look at surfaces of revolution, there's your x-axis, right? And then rotate this thing around. Actually, the curves I'm drawing in are geodesics here. If you go to the local mins and the local maxes, at the curve that you're revolving around the x-axis, those are geodesics. None of the other circles are, by the way. What's analogous to this is if you're on a sphere, the equator is a geodesic, but if you go up here, this is not a geodesic. Okay, that's actually you're curving. Now it's not intuitive until you get a tiny, tiny little circle around the North Pole. That's obviously curving. If that were the North Pole right there, and I do this, obviously I'm curving to the left, right? Even though it's a constant line of latitude, right? And so the point is, if I go around a line of latitude around the North Pole, I'm curving I'm curving that way, right? If I go around, let's say similarly, I go around this way, right? Now I'm curving towards the South Pole. Here I'm curving towards the North Pole. Here I'm curving towards the South Pole. So in this case, I'm curving this way. In this case, I'm curving that way. But if I'm at the equator, I'm not curving at all, right? So the lines of latitude here are curving that way. And this line is curving that way. Okay. By the way, it doesn't matter if I'm going around like this or going around the other way. The curvature vector is the same. Why? Because if I replace t with minus t, second derivatives don't change, right? Because the second derivative is you take the derivative vector t, and then you do it again. So you get minus 1 times minus 1. That's plus 1. Okay. So if I replace t with minus t, then instead of going one way along a curve, I'm going the other way around the curve. The t, the velocity vector, that changes by a sign. A prime of t changes by a sign because that's one negative 1. But a double prime of t, think of it this way. What is alpha double prime of t? This is the second derivative of alpha with respect to dt squared. If I change t by minus 1, dt changes by minus 1. Minus 1 squared is plus 1. And so this actually doesn't change at all if I go the other way. So in both cases, geodesic curvature doesn't care which way you're going. Or I should say, your curvature vector, alpha double prime of t, doesn't care which way you're going. By the way, this demonstrates something kind of interesting about curvature. Because what we've demonstrated is that these lines of latitude are curving away from each other. Do you all see that? This line of latitude and that line of latitude. They're both curving towards their closest pole, right? This one's curving towards the North Pole, that one's curving towards the South Pole. So you have an example of two paths. Imagine two people. One is here and one is here, right? And they're walking around these lines of latitude. They're both curving away from each other, but they're not getting any further apart. Isn't that weird? They're curving. Normally on a flat space, right? If you and I are walking next to each other and then I don't like you or something, then I start to curve away from you, right? I get further away from you, right? But imagine if you're curving away from someone, but you're not getting any further away, right? How can that be? Well, that's one of the effects of curvature. You're on a curved space. So that's actually an effect of Gauss curvature. It's also connected to gravity. I think I made this point before. Did I show you all that picture before about curving away but not getting further apart? Did I ever? Is that familiar? No? Okay. So let me tell you how it's relevant for understanding what gravity is. I know we talked about gravity a little bit. But, and this is one of the most mind-blowing ideas. Like if you ever really want to just blow someone's mind, explain this to them, all right? I mean, this is a pretty deep idea, right? Is that gravity is not a force, right? And it even bothers me when I hear physicists talk about the force of gravity. I'm like, but it's not a force. I mean, I'll say the words force of gravity every once in a while, but then I feel compelled to say, by the way, it's not a force. It's a phenomenon. It seems like there's a force, right? Well, what's pulling me down? Must be gravity. Must be a force of gravity. But no, there is no force of gravity. We're in an accelerating frame of reference, right? And I'm sure I said that before, right? Did I say that in the first week? But just to repeat, imagine you went into an elevator and got abducted by aliens, and they took you into outer space, and you're locked in the elevator, but they had stabilizers on there, so you had no idea you were being abducted, right? You think you're on the Earth with 1 g of gravity, but in fact you're in outer space being accelerated at 9.8 meters per second squared towards their home planet, which is pushing you down. The acceleration is pushing you down in the elevator. You wouldn't be able to tell the difference. You would think you still have 1 g of gravity, right? You wouldn't realize that you're in outer space because the elevator is being towed by the spaceship and being accelerated at 9.8 meters per second squared. And then Einstein's insight is, wait a second, you wouldn't be able to tell the difference. So I guess this must therefore be the same thing. So we are in an accelerating frame of reference, just like inside the elevator, going up at 9.8 meters per second squared. And then people are like, a natural reaction would be for someone to say BS, right? Like, no way, stop it, that's ridiculous. I can look out the window, I'm not going anywhere, I'm completely at rest. And then you have to explain to them, no, everything you see out the window is also accelerating at 9.8 meters per second squared up, right? And then the logical thing they're going to say is, look, if the Earth were flat, you could take a flat disk and you could accelerate the whole thing at 9.8 meters per second squared, and that at least would be consistent. But the Earth isn't flat, it's round, right? And how can we be accelerating this way, and the people on the other side of the world are accelerating that way, but we're not getting any further apart? How is it possible to accelerate away from someone and not get any further apart? That's how. If you're on a curved space, these two curves are accelerating. The difference, these are spatial curves. We're talking about curves in the space-time, right? So it's being a little metaphorical here, right? But technically, my world line, the curve I'm tracing out in this four-dimensional space-time manifold, right? I'm not a point, I'm a curve, right? Each point in time, I'm a point. But since for each value of time, I'm at a different point in the space-time. I'm a curve, actually, in space-time. And so are you, idealized as a curve. My curve and someone on the other side of the world's curve, we're accelerating away from each other, but we're not getting any further apart. For example, and the reason is because of the curvature of the universe between us. And you're like, what? Right? And of course, that's Einstein's great idea, right? That matter curves space-time. The Earth is a very massive thing, and it curves space-time. And so this is the simplest example of curvature would be a sphere. It's a simple example of something that's not flat. And then you can get this phenomenon of two things accelerating away from each other, but not getting any further apart. And by the way, if they're like, yeah, okay, well, I refuse to accept this, but I think I said this, but it wasn't just like if you explain this to a friend and they're really truly listening, they should call BS and they should be skeptical, right? Like I don't even want someone to be so trusting that they just take your word for it or take my word for it, right? You shouldn't. You should be like, no way, right? And guess what? The scientists of Einstein's era were exactly that. A majority of them, I think, in fact. And sometimes they might even be a little rude to him, right? It took a long time. I don't know. I would be curious to know like what year the majority came around to Einstein's way of looking at things. I know that there were a few early adopters like Hilbert and Eddington, and so some of the most brilliant people on the planet were like they saw it, like they got it. Like, but you had to be a genius to even understand it is the problem, right?
How did he find funding?
Oh, who, Einstein?
Yeah.
Well, famously, he didn't.
Oh, cool.
So if you're ever like wondering, and by the way, I think it's an inspirational story. Albert Einstein was Jewish, and he got his PhD, I think, in Germany, I think, and then he couldn't get a job. So like, if you ever go get a PhD and can't get a job, well, you and Einstein, you're in good company, okay? couldn't get a job, right? And so he got a job as in Switzerland working in a patent office, right? He was sitting there approving or reviewing patent applications, right? And apparently he wasn't a very good employee. He was mostly off in the corner working on his research, right? So he actually found funding sort of indirectly. And I'm kind of curious. That would be, why isn't there a movie about that? That's a pretty amazing story, right? What was that job interview like? What were his fellow employees like? He doesn't do any work. He just is in the corner doing weird stuff. Okay. I mean, how did he do that exactly? I would like to know, to get the details of that. The history of this is super fascinating. But then apparently, in that year, he had a miracle year. He did, his back was against the wall, I guess. He knew that if he didn't do something great, he wasn't going to get a job in academia ever. And so then he did three great works. One of them was special relativity. Yeah.
So if gravity, you were saying, is this sort of a phenomenon that we experience because of curvature, but it's not a real force.
Mm-hmm.
What forces are real?
All the other ones, well, supposedly. I mean, that's
supposedly,
right. That's a good question.
Could they also be some sort of curvature, do you think?
People experiment with. I mean, it's a natural question you ask, and it's a natural idea to wonder about. But I don't know of any successful theory that is able to treat these other forces the same way we can think of as gravity as a phenomenon, not a force.
Okay.
But that doesn't. I mean, look. It doesn't. Okay. There's a word called a paradigm. Y'all know what a paradigm is? It's the things that you don't even know you're assuming, right? Like the Newtonian paradigm was that you had space, X, Y, and Z, and then you had time, which was something completely different, and you had, of course, it's different, right? And then that's how we think. That's normal and natural for us, right? Space and time are two different things, and that's how Newton understood it. That's your multivariable calculus problems are all in the Newtonian paradigm. And then Einstein came up with a new paradigm and said, no, there's no space and time separately. There's something called space-time, and you can rotate space and time into each other. And guess what? It works more accurately than the Newtonian theory. And the Newtonian theory is simply wrong in terms of gravity and so forth. So it would appear that, special relativity and general relativity. Special relativity unifies space and time into one concept called space-time, and general relativity talks about how matter curves that space-time. All right, and so we're studying two-dimensional surfaces, also known as two-dimensional manifolds in this course. We live in a four-dimensional manifold called a four-dimensional space-time. Okay, there's a minus sign in the rule of Pythagoras. We're not going to do that in this class mostly, but so with that paradigm. The reason we celebrate Einstein is because he was at the center of shattering Newtonian paradigm, right, and coming up with a new paradigm. And so then you ask me, is it possible that maybe we could come up with a yet better paradigm, right? And I hope so. That would be amazing. That would be awesome. Can we come up with a new paradigm where not only is gravity not a force, but all these other forces aren't forces too? And it's just, or what is this? That would be amazing. But you're asking, I'm a fish swimming in water, and you're asking me about the water, and I don't know about the water, right? Or we think air is vacuum, but actually it's stuff, right? The point is, how do I know what I don't know, right? That's the, how do I know which of these assumptions I'm making to question? Because I don't even know I'm making the assumptions. So at least we can, if we have the concept of a paradigm and that we probably are making assumptions that aren't valid, and don't even realize it, then I think that's great. That's a good sort of reality check. Keeps us all modest. At the same time, it doesn't mean every proposal for a new paradigm is right. In fact, let's face it, most of them are wrong. Right? So we have to do two things: stay modest and realize that probably every physics theory that we know is fundamentally flawed, and realize at the same time that it is, after all, the best we got. Okay, so it's not like it's worthless or something. It's just it's the best we got, and we got to go with the best we got, right? I mean, what else are you going to do, right? And people come up with all kinds of cool theories, and I love entertaining these new theories. I think it's so much fun. But of course, 999,999 out of a million of them are going to be wrong. And we get an Einstein. And by the way, it's not even Einstein. We give Einstein way more credit than he deserves, because it's a handy little, it's handy dandy way of taking some ideas and associating. We got to name the ideas, right? But the more you study the history, by the way, the more you realize that, gosh, I mean, he was just at the center of it, and he's of course did great. But it's a team effort. I just want to make sure everyone realizes that if Einstein had never been born, we'd be talking about general relativity today. I would say that he accelerated. He might have. Look, I think I'm giving him a lot of credit if I say he accelerated by 20 years. Okay, that's being generous. Lorentz was doing stuff with special relativity. I mean, he had all the formulas. He just didn't have the paradigm. You know what I mean? And he sort of, and he realized with Einstein when he was coming up with the equations, he was talking to mathematicians, and Hilbert probably wrote down the Einstein equation before Einstein, and Einstein felt, it was. And then also there are precursor theories to general relativity you can look at. It's like, oh, that's a nice idea. Like if you actually study the history of ideas, people were coming up with really nice ideas, and so it's. And I think it's good. The reason I'm not trying to put Einstein down because I consider him the greatest physicist of all time. So just for the record, right? But the reason I think it's good to have a realistic image is that if we have this unrealistic thing we build up, then we might all think we couldn't possibly do that, right? And the answer is, yeah, of course you couldn't possibly do it, but you could be part of a team that might do something even better, right? So if you think of it that way, then actually it's quite attainable. Okay, so anyway, that's curving away, not getting further apart. I could easily spend the rest of this talk talking about paradigms that don't work. Right? But it is fun, right? Because kind of gets into philosophy. Right? I'm going to just mention one. Witten, who holds Einstein's chair at the Institute for Advanced Studies, has suggested, he said out loud, that he thinks maybe space-time is an emergent phenomenon, meaning that there isn't such a thing as a space-time. Now, I study curvature of space-time, so I'm like, what? And by the way, he's done some contributions to general relativity too, okay? But he's mostly a string theorist. But there is this thing called this conformal field theory, ADS-CFT. So you might study that, the anti-de Sitter space conformal field theory, duality, or whatever it's called. You can Google that and study that. And what's interesting is that's just sort of a hint at how they show how two theories, one theory in a four-dimensional space-time is equivalent to doing calculations on the boundary of the space-time. And so, in other words, you don't somehow or another there's a duality between the theories, and so you can, in other words, if you have two physics theories that are equivalent and they take place in two different manifolds, but there's a dictionary between the two, right? There's an equivalence. Then you can solve the laws of physics in one universe, and you're also solving the laws of physics in another universe. And so, what if we're actually solving the laws of physics somewhere else, but it's completely in one-to-one correspondence to what we perceive as our space-time? I think that's kind of where what the idea is, okay? And so, but let me also say that I think that might be complete and utter nonsense also, right? But it's a cool idea, right? It's a cool idea that fundamentally the universe, like if you ask what's the next paradigm shattering idea? If it turns out that space-time is not real, it's a fake, right? It just seems like there's a space-time. Well, clearly that's a new paradigm, right? Like there's no space-time manifold. It just seems like there is, right? Okay, that would be an example of a new paradigm, and we got to put it on the list of possibilities. And that would be pretty amazing if that's true. But that's a pretty good example of sort of an out there idea. String theory, of course, famously also postulates that there's super tiny, dimensions, 6 curled up dimensions, called a Calabi-Yau manifold, that we can't see, and has never been measured, never been detected. And that also is an amazing idea, that there would be tiny curled up dimensions, right? And us mathematicians, we love that. That would be so neat if that were true. If either of these things are true, that is just going to be amazing. But we're speculating about things that are beyond our ability to experimentally verify or to really fully understand. And so these theoretical physicists, it should be stated for the record that they are way out over their skis. Okay? Let me put it this way. If Einstein wrote down G = 8 pi t, the Einstein equation, and there was no experimental data to back it up. In other words, you didn't have the anomalous orbit of Mercury, or you didn't have the bending of light around the sun as predicted by general relativity and not Newtonian physics. If you didn't have any experimental data for it, if you didn't have not detected gravitational waves, and you didn't have evidence for the Big Bang or the accelerating expansion of the universe, if you didn't have any of that data, right, then you just have to say probably not. Like you can't. It's just too. You would say it's a beautiful theory, but there's too many beautiful theories to choose from, and how do you know which beautiful theory is correct and whose notion of beauty is correct, right? And so it's very interesting. It gets into philosophy, and because isn't Newtonian physics actually quite beautiful as well? Yeah, it's beautiful. Love it. It's simpler. Why are you making it so complicated, Albert? What's that?
It works most of the time.
Yeah, Newtonian physics works most of the time, right? And so the point is, even Albert Einstein wouldn't have tried to come up with special general relativity if Newtonian physics had been working, right? No, it wasn't working. It wasn't working, right? That was what? They measured the speed of light, the Michelson-Morley experiment, 1889, and Newtonian physics wasn't working, right? And so out of necessity, you come up with a new paradigm. And so I think it ultimately, when I interpret the history of science, I'm not a historian, but with the little bit I know, it's like ultimately we got to settle this with data, right? And if you say, but beauty tells me the answer is this, you're making the same mistake that I don't know what Aristotle. Who was it? Aristotle? Who was the guy who's just assumed that if you dropped a heavier thing out of a window and a lighter thing, that the heavier thing would hit faster, and never bothered to do the experiment? Was that Aristotle? Yeah. Never bothered to do the experiment. Right? It's like, heavier thing, something falls proportionate to their mass. It's just wrong, right? All you got to do is just test it. Come on, get a heavy thing, get a light. They have air resistance is the problem, right? You need 2 rocks, right? But don't do a feather, right? But take a big rock and a smaller rock, right? You drop them, they hit the ground practically at the same time. Air resistance is the only effect, right? And yet that was considered science for a long time because no one bothered to do the experiment, right? And I think let me just say for the record that theoretical physicists today are. If you just go based on what seems right and what would be beautiful, right? Ultimately, there's too many beautiful things to pick from, I guess. But on the other hand, there is such a thing as beauty, isn't there? I'm not lying, right? I'm not lying. There's such a thing as mathematical beauty. And when you really truly understand the universe, it does seem to have a beauty to it, at least some of the time. So we can't ignore that either. So, I'm not, that's where things are. Okay. Other examples of geodesics, let me just give one more example. Take a cylinder. And then Now, suppose an ant is walking along a cylinder. Obviously, all these circles, like this circle right here, is a geodesic. You agree? Just sort of like the equator. But also, you can have sort of a spiral, right? On that is also a geodesic. And let me tell you why. Here's what's interesting. Take a piece of paper. That's a geodesic, right? Any straight line. Now curl it up into a cylinder, and that makes a spiral. Okay? Or part of a spiral. And so, one loop around, if I just fold it up like that, right? And so then you can keep on going after that. So, one thing that's interesting about geodesics is that they're intrinsic geometry. There are no L, M, and N's. Remember I said that geodesic curvatures function EF. There are no L, M, and N's in there. This is the key point. It's what we proved last time. And so it's intrinsic geometry, which means that whether or not, this cylinder is rolled up or whether it's laid out flat, it's locally the same geometry. Isn't that cool? And so I can understand that it doesn't make any difference. The F and G's don't change. I can use the same coordinate chart. Go ahead and take a cylinder, but then remove a neighborhood of that line right there. Okay, so kind of cut along that line, right? Okay. So I'll just talk about geodesics that don't go across that line. Then I can use a coordinate chart, one for here and one for there. I can use, in some sense, the same coordinate chart. So think of it this way. I can have a UV coordinate chart for this guy, right? I can then have a mapping that goes over there, right? If I compose the mappings, then I have a mapping from this coordinate chart over there as well. You guys good? Now the mapping from here to here, I want to do it in such a way it doesn't stretch anything, doesn't distort anything. And so the point is, whether I look at this coordinate chart mapping here, which is the composition of these two maps, or this coordinate chart mapping, I get the same EF and G's over there. By the way, if you get the same EF and G's, you call this mapping right here an isometry. Okay, I told you what an isometry was intuitively, right? Just wrap it up, don't change distances at all, right? Just do the natural thing where you don't stretch the piece of paper at all. Isometry, by definition, is a mapping from one surface to another, such that if I take this coordinate chart, take a coordinate chart for this surface, compose it with the mapping, I get a coordinate chart for that surface and the image of this mapping. And if the EF and G's here are the same as the EF and G's for this one, then we say that that's an isometry. Fair? By the way, that's something we're going to learn later on in the book. I was for after spring break. There's another interesting case, by the way, and that is really you should always look at the EF and G's in a certain way. Remember what EF and G's are? So what I just got through saying is, let's call this mapping. Let's call this mapping here. We call this X of UV, right? But X of UV. And then we can call this one here Y of UV, okay? I think that's what the book usually does. And so then we can talk about the E, F, and G's. By the way, the reason I do it in a 2x2 matrix is that remember what E is, right? E is XU dot XU. And so this is like the U direction, that's the V direction, that's the U direction, that's the V direction. This is XU dot XU, this is XU dot XV, that's XV dot XU, and this is XV dot XV. Okay, so it's natural to think of it as a matrix action. And then so we say it's an isometry if EY, GY, then let the FYs here, right? If these are equal, right? If you get the same EF and G's, then we'll say that this mapping is an isometry. There's another case, which is instead of an isometry, we can call this a conformal mapping. A conformal map. And that's when you look at them as matrices, the matrices are the same up to a factor, which up to a function. So in other words, that's matrix multiplication of a function. It's a phi of u comma v here. Okay. So if you're changing the EF and G's, but only by a uniform factor at each point, at each point, E, F, and G each get scaled by the same factor. Okay, I don't care what it is, as long as it's the same at each point. But this is a function of u and v. That factor can change point to point. You guys get the idea? Then we call that a conformal mapping. In the case that you have a conformal mapping where the conformal factor, this is called the conformal factor, phi. And in the case the conformal factor is 1, then it's isometry. Okay. Now you might say, why are we interested in conformal mappings? Well, why not? Right? And can we agree that's like isometry is clearly an important thing? And so then you say, okay, well, what's something that's not an what? Okay, you know what isometry is. You're just not bending or stretching anything. Okay, this is like give me an example of something that's not an isometry, but still might have an interesting geometric property. Well, that would be the next easiest thing to say, right? Unless you got a better idea. Okay. And by the way, guess what? What you're effectively doing is you are stretching the metric by a factor. And I'm going to give you an example of such a metric. And then I'm going to wish you have a good time on your spring break. By the way, no homework due Friday. Did you guys get the email? Wasn't that nice?
Thanks.
Yeah.
Thank you.
Yeah. I was like, you know what? You guys did pretty well on the test. We're good to go. Okay. So I'm going to give you an example of a conformal metric. And that is, what if you have dx squared plus dy squared plus dz squared? Okay, now that's a three-dimensional, that's the standard flat metric on three-dimensional space. Okay, now, if you like, what we're doing there, this is saying my EF and G matrix is actually this, okay? That's like saying E and G are both 1 and excuse me, E and G are both 1 and the F is 0, but we're going to do in a three-dimensional way. Okay? So let's not worry about notation just yet. In fact, you know, why does that represent the flat metric? That's the identity matrix, right? The point is, if I say what is, instead of XU and XV, right? What we want to be talking about is, let's say, remember XU is as an operator is DDU, right? And this would be like DDV as an operator, right? So as a directional derivative, right? And then let's just think of this as ddx1, and we'll think of this as ddx2, and that way we can have a third one, which is ddx3, right? Okay, so that's where how the notation changes. And you start thinking of vectors as operators. And so then this identity matrix, we're simply saying that when you take the dot product of ddx I, dot product ddxj, that I want this to equal 1 if I equals j, right? And then 0 otherwise. Okay, and that's known as a Dirac delta function, right? Okay, and so that's that's our normal dot product, if you like, right? That's saying that I dot k is 0 and I dot j is 0, but I dot I is 1. Okay, and then this is the symbol for it, and so what you can do is you can then say another symbol for it would be just write down the Dirac delta function, delta ij. You could say this is the metric, this is the flat metric if you like. So this is one way to do it. Okay, now how would I get a metric conformal to that? Well, you could just multiply by some function. Okay, just take some function of x, y, and z, and the function I want to show you is 1 plus m, some constant m, over 2r. Okay. And this is where r is equal to the square root of x squared plus y squared plus z squared. And so, whereas we had this flat metric here, okay, and this is the origin. By the way, this is going to be R3, okay? I've drawn it as R2, but I'm going to think of it as R. It's R3, but I'm drawing it as R2 because I don't have a four-dimensional space to draw it in, okay? The flat metric, if I just have delta ij, flat metric in R3, that's what you did in multivariable calculus. But now notice that 1 over r is blowing up at the origin, isn't it? Right? This factor is going to 1. This factor is going to 1 in the end, but it's going to infinity as you get close to that point, right? And it turns out that the way that you actually can, what you get is something that blows up. And so if you just take a parabola, it turns out for this particular metric, which I am an expert on, you'll wonder why in just a second, it actually blows up this origin. You have to remove, when r equals 0, it goes to infinity, right? So really, let's take R3 minus the origin, okay? And then when you blow up that factor, actually what you get is another end, by the way, so it happens. You get two asymptotically flat ends. You get an R3 here and an R3 here, and it's connected by a neck. And what I've just drawn for you here is if you do this in 4 dimensions, make this x, y, and then z, and then have this be w, and then look at the parabola here, norm of x, y, z, call it r, right? Equal to w squared over 8m plus 2m. You guys, if you turn your head like that, that's a parabola, right? And then you rotate around the x, y, and z directions. These are 2-dimensional spheres here, right? Turns out this metric on that rotated parabola is isometric to this flat metric when you put on that conformal factor. Okay? So this is a nice sort of way of, we can look at this curved space, but it is in fact just this. And what this is, by the way, is the t equals 0 slice of Schwarzschild, which represents a non-rotating black hole. And this minimal neck right here is actually the apparent horizon of a black hole. So that's what a black hole looks like in some sense. Right? It's actually, the apparent horizon is actually a minimal surface. And of course, this is just a 3-dimensional slice of a 4-dimensional space-time representing a black hole. And we can talk about the 4-dimensional space-time some other time. But maybe this would be my favorite application of a conformal metric, right? Is this the t equals 0 slice of a Schwarzschild black hole is in fact conformally flat. And so, have a nice spring break.